if you have d-dimensional feature vector, okay, so that means that it is a vector, column vector. A vector is generally a column vector, okay. So I can write x as x1, x2 to xd, where x1 is one feature, x2 is the second feature, x3 is the third feature, and so on, okay. So in the previous class, I mean, in the previous session, we talked about that distinguishing between fish, right, based on length, lightness, width, shape of fins, and all that. So each of them can be x1, x2, x3, and so like that you can have d features, okay, which you can talk to get a d-dimensional feature vector, okay. Then you can define a matrix, something like this, with rows and columns, okay. All right. Now, all of you know what a symmetric matrix is, okay, right? And diagonal matrix, okay. That means only, okay. So, all right. All of you are also familiar with matrix multiplication. So if you multiply a matrix with a vector, you will get a transformed vector, okay. And this is the way matrix multiplication. So in pattern recognition, okay, generally vectors are highlighted in small letters, bold, okay, and matrices are actually highlighted in capital letter, bold, okay. This is generally a notation convention that is formed, okay. So this matrix multiplied by this vector giving you the output vector is matrix is capital M, okay, and vector is denoted by a small letter, bold X, and the output vector is also small letter, bold Y, okay. And you also know that, okay, the matrix multiplication has to be compatible, okay. So for example, if you have say 4 cross 3 matrix, okay, you can multiply with a 3 cross 1 matrix to get a 4 cross 1 vector, okay. Likewise, you can take a 5 by 5 matrix, okay, and multiply it with 5 by 1 vector to get a 5 by 1 vector, okay. So that is quite straightforward, which you should know, okay. Okay, there is something called as inner product, okay, which is x transpose y. And can anybody tell me, inner product is nothing but dot product, okay, between two vectors. So generally the dot product, is it always a scalar or is it a vector? Can anybody tell me? Hello? I'm asking a question.
It's a scalar.
Yes.
Right?
Scalar, sir.
It's a scalar. It's a,
yeah.
Okay, fine. Then you can find out the norm of a vector, okay, as square root of x transpose x, okay. And then you also know that inner product or dot product in two vectors is mod x mod y cos theta. So from there you can get the angle, okay, between two vectors. You also have, because cos theta modulus is limited, is less than equal to 1, okay, you can actually write this Cauchy-Schwarz inequality, which is mod x transpose y is less than equal to mod x mod y, okay. All right. You also should be familiar with independence of vectors, okay. So what it means is that if there are some vectors that span the space, and okay, if no vector can be written as a linear combination of such vectors, then you say that they are independent, okay. All right. So for example, our 3D space, okay, with the Cartesian coordinates of 0, 0, 1, 1, 0, 0, and 0, 1, 0, right? That is independent, okay. The vectors are all independent of each other. So they form a basis vector, okay. All right. One thing, please remember that in a 3D, in any space, okay, there is no unique set of basis vectors, okay. As long as you choose any d-dimensional vectors which are whose linear combinations cannot be expressed, okay. But I mean, what I'm trying to say is that no single vector, okay, can be represented as a linear combination of these vectors, then you say they are linearly independent, okay. Similar to inner product, there is something called as outer product, okay, which is xy transpose. So what do you think XY transpose would be? Will it be a vector or will it be a matrix or will it be a scalar? X is a vector, Y is a vector. Quickly tell me, participants, please tell me whether it's a
vector. It's a vector.
No. Think and tell me. XY transpose. So X is D cross 1, D dimension. Okay. And what is Y? 1 cross D. So D cross 1 vector multiplying with 1 cross D vector. What do you get? D cross D. Okay. You will get D cross D. Is everybody clear? See, yes. Supposing X is 2 dimension, Y is 2 dimension. Okay. X is 2 dimension. Y transpose will be 1 cross 2. Okay. So 2 cross 1 gets multiplied with 1 cross 2. Okay. So your dimension of the resulting matrix will be 2 cross 2. Okay. So just remember that outer product of two vectors is always a matrix. Okay. And there is something called as a rank, okay, of a matrix, which is number of independent rows and columns of a matrix. And you can verify this, that outer product between two vectors will always be a matrix of rank 1. Okay. So this you can actually, you take any two vectors, take its outer product. Okay. You will see that the rank is 1, meaning that there's only one independent row or column, and the other rows and columns are actually scalars of that, scalar multiples of that. Okay. All right. Now, there is something called as a scalar function. Okay. So scalar function is like x1 squared plus x2 squared, or xy, or x1 squared plus y1 cube plus z1 squared. Okay. Something like that. Okay. So with regards to that, you can actually derive what is called as a gradient. Now, this is something very important, not just in this machine learning course, but even in the deep learning course, which you will be covering, most of you will be attending 3 weeks from now. Okay, we will talk about something called as a gradient of a function. That's why I'm covering it here, okay, as a basics. So gradient means what? You take a function x is of multiple variables. Okay, like say, you know a function f of x, right? How many variables are there in f of x? What is the independent variable in f of x? What is the independent variable in f of x? F of x, f of small x. Yeah. Anybody
X.
please tell x. Okay. Now, let me go to f of x1 comma x2. Okay. F bracket x1 comma x2 close bracket. How many independent variables are there? 2 variables, x1 and x2. Okay. Likewise, f of x1 comma x2 comma 3. Okay. How many independent variables are there? 3. Now, those x1 comma x2 x3 is what you're writing as a vector x here. Okay. So as many independent variables, you take their individual gradients and partial derivatives you take. Okay. So dou fx by dou x1, dou fx by dou x2, dou fx by dou xt. If they are d variables, okay, you take the partial derivatives. Is it clear to everyone? So,
sir, excuse me, sir.
Yeah.
Sir, sorry to disturb you. Sir, PPT is not visible. Could you please check out once?
Oh, it's not visible. Yeah, I'll just check. It suddenly went off, or was it not visible from a long time?
Long time.
Oh, then you should tell me, no? Okay. Okay, anyways, we will just quickly go through it. Okay. Rank of a matrix is clear, no? Outer product, all that. You saw the slides, or did you lose out there? Which slide do you want me to start from?
So from the rank of or linear
Okay.
independent
So
vector basis.
from here. Okay. So just read this quickly. What I'm saying is any vector, okay, if you have a set of vectors, they are linearly independent if no vector can be written as a linear combination of them. Okay, right. And outer product of two vectors gives a matrix, I told you. Okay, xy transpose, x is d dimension, y transpose is also d dimension. So d cross one vector multiplies with 1 cross d, okay, to give you d by d. Okay. The next is rank of a matrix, okay, is number of independent rows and columns of a matrix. And I also told you that the outer product between two vectors will give you a matrix of rank 2, okay? Oh, sorry, rank 1, okay? All right. So I was talking about gradient of a scalar function. Is the slide visible?
Yeah.
Hello?
Yes,
Okay.
yes, it is visible.
It's visible,
It is
right?
visible, sir. Visible.
Yes,
Okay,
sir.
okay. So
Yes,
fine. So I'm saying that there is a scalar function f of x, okay, and x is like x1 comma x2, x1, x2, x3, already like that x1, x2, x3 to xd. So you take the scalar function will have d independent variables, okay, x1 to xd. So you take the partial derivation of that function with respect to each of the independent variables, okay, like dou f x by x1, dou f x by dou x2, dou f x by dou xd, okay, and vector x is what? x1, x2, x3 till xd. So gradient of a function, what is it? Is it a scalar? Is it a vector? Is it a matrix? Look at this and tell me. It will be a, is it a scalar or is it a vector? Hello?
Scalar.
Scalar.
No. See, I'm taking the derivative with respect to each of the variables, right? And I'm stacking them into a vector. So what will it be?
Okay, it will become a vector. Indivisible is a vector.
Vector.
Okay.
Yes. Okay. So gradient is always a vector. Okay. Gradient is a vector. Okay. So gradient is a vector. It will have a magnitude. It will have a phase. Okay. That is not important. But remember that gradient will always be a vector function. Okay. It will always be a vector. Okay. All right. So this is not required right now. But anyways, if you have a vector valued function, okay, then you define what is called as a Jacobian. Okay. So meaning if you have multiple functions, see, here the function was only f of x. Okay. Supposing you have multiple scalar functions like fn of x, f2 of x, f3 of x, okay, of multi-dimension variables. Okay. So then you can define what is called as a Jacobian, okay, which is something like this. Okay. So anyways, once we do neural networks later on, we will come across this, but just to mention it. Okay. All right. Now, this is very, very important. Okay. I want you to actually go back and derive this, or even if you're not able to derive, look at the Wikipedia or any matrix algebra book and try to derive it. Okay. So remember that what is mx over here? What is mx? Capital M is what? Matrix. What is x? X is a vector. So if you multiply m with x, what will I get?
Matrix.
I will get a vector. No, I'm multiplying a matrix with a vector. What will I get?
Vector.
Vector. And I'll take dou by dou x of that. Okay? Dou by dou x of that. So essentially, I'm taking a gradient of a vector function, so which is like this Jacobian. Okay? So that is equal to m. Okay? Then dou by dou x of y transpose x. Okay? What is y transpose x? It is a scalar or is it a gradient? It is a scalar.
Scalar.
Inner product, right? So, so dou by dou x of x transpose y is equal to y. Okay. Now, please remember that anything bold is a matrix or a vector. So this is matrix M, okay? So if I take dou by dou x of mx, and remember x
Sir,
is
I
not
have
a
a
scalar, it is a
question.
vector.
Sir, I have a
Yes,
question.
yes,
Sir, what is the significance
yeah.
of this matrix or vector derivative?
So whenever you do, so see, I told you now that there is a cost function or there is an empirical risk minimization. I told you, no, just before we left for lunch. So generally, that vector, that particular function is generally a scalar function. Okay, all right. So it will be in multiple dimensions, not just in one dimension. So you have to use principles of matrix and vector derivatives to take the derivative, okay, to minimize and find out the optimal value. Is it clear, or you just hang on? Okay, I will shortly, just about 10 minutes time, I will give you an application of this in regression. Okay.
Okay, sir. Thank you.
Okay, sir.
Okay, fine. So remember that this is very important, because why I'm saying that is, see, in any classifier design, okay, you will design what is called as a loss function. Okay, and what is the goal of the classifier? The goal of the classifier is to minimize the loss function. I already told you that, right? That is like empirical loss. I told you, na? Okay, so this loss function is generally in multiple dimensions, not just single dimension. Okay, and it is a scalar function. Okay, so I will use concepts like derivative of that with respect to scalar function, which is gradient. And if I have multiple functions to optimize, then I will use Jacobian and so on. Okay, so that's the reason why this is important. Okay, all right. Dou by dou x of x transpose mx is equal to m plus m transpose x. Okay, so you will have to remember that also. See, if we were doing it in a very conventional class, right? Meaning, like if you were doing this class for an exam, then I
Sir, you are not audible.
Manchare sir. Hello.
Sir,
Is there any network problem?
yes, sir.
Sir lost the connection, I think so.
Okay, okay. You please check it once.
hello.
Yes, sir. Audible.
Yes, sir.
Yeah. Actually, there was some problem in the net. It is going on, coming. Okay, so let me just share it again. Okay. Yeah. So I was actually talking about this matrix derivatives, right? Before the line went off. So what I'm telling you is that these are all very important, okay, for pattern recognition, because you actually design cost functions or loss functions to optimize your network, okay, and in doing so, you actually design scalar functions, okay, and so the scalar function is multi-dimensional function, okay. So you actually take concepts of vector derivatives and so on, okay, in order to solve your problem. Okay, so that is why this gradient and everything are very important. Okay, so we will actually in the course, okay, in the course we will give you an example, okay, of how to do this type of derivatives, okay, for the application of regression. Okay, so that we will cover in this lecture itself. Okay, so you don't need to worry about that, but just understand that that with respect to matrices and vectors, you can take derivatives. Okay, so that's important. Can I proceed? Hello, can I proceed? Or do you have any doubts? Okay, fine. Okay, and most of you are familiar with eigenvalues and eigenvectors, right? I don't need to explain it. Okay, it's applicable for a square matrix, and a square matrix with full rank will have m eigenvalues and corresponding m eigenvectors, and the eigenvalues and eigenvectors can be used to diagonalize, okay, the matrix as shown. Okay, so this is something you people should be familiar with. Okay, the other part is whenever you have a square matrix which is rank deficient, okay, and if it has a rank of R, then there will be R independent rows and columns that you know, right? So there will be at most R independent eigenvectors, okay, and R non-zero eigenvalues. Is it clear to everyone? Okay, and the remaining R n minus R eigenvalues will be 0. Okay, all right. And most of you know how to compute the inverse of a matrix that you compute. Okay, so by using an adjoint and so on. Okay, adjoint by determinant and so on, you get the M inverse. Okay, now what you see below, okay, is something like M transpose M inverse M transpose. Okay, this is what is called a pseudo inverse, and this is exactly the solution that you will get when you solve a regression type of problem. Okay, and that is what I'll be covering right now. Okay, there are some things called orthogonal matrices and all that, so hopefully that should be covered in the PCA part. So nevertheless, I'll just tell you, if you have m vectors whose inner product is 1 with each other, but between each other it is 0, okay, then you say that it's an orthogonal matrix. So how many of you have heard of DCT, DFT, and so on in signals and systems? Hello?
Everyone.
Are you able to listen? How many of you heard of discrete Fourier transform in signals and systems?
Yes, sir, we heard, sir.
Yes, sir.
Yeah. So those all belong to what are called as unitary transforms or orthogonal transforms. Okay. So that means if you take any two basis functions or basis vectors of the DFT, okay, they are orthogonal to each other. Meaning, if you take two distinct eigenvectors, two distinct basis vectors, okay, their inner product will be 0. Whereas if you take the basis vector inner product to itself, it will be 1. Okay, so that's why I'm writing here Qi transpose Qj is equal to 1. Okay, if I is equal to j. Okay, and 0 otherwise. Okay, 0 when I am not equal to j. Okay, in fact, your Cartesian coordinates basis functions like 0, 0, 1, 1, 0, 0, 0, 1, 0. You know what I'm talking about, right? In R3, okay, what is one possible basis function, basis vectors? It is 0, 0, 1, 0, 1, 0, 1, 0, 0. They actually are orthogonal, okay? Because 0, 0, 1 inner product with 1, 0, 0 is 0, okay? Similarly, 1, 0, 0 inner product with 0, 1, 0 is 0, okay? Then 0, 1, 0 inner product with 1, 0, 0 is 0, okay? And inner product of 1, 0, 0 with 1, 0, 0 is 1. Okay, you understand now what I'm saying. So in your R3, okay, the conventional Cartesian coordinates of 0, 0, 1, 0, 1, 0, 1, 0, 0, they are all orthogonal to each other. Okay, all right. Okay, there is something called as positive definite matrix. Okay, which means that X transpose AX. X is a vector, A is a matrix. And for all possible vectors, if X transpose AX is greater than or equal to 0, we say A is a positive definite matrix. Okay. And it has some, there's something called real symmetric matrix. Anyways, these things are not very important. Okay. What is more important for today's class are these. Okay. Matrix and vector derivatives, especially vector derivatives. Okay. Or gradients. So that is what we will be covering in right now. Okay. So, are you all able to understand so far? Can I proceed?
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Okay. So I'm done with the introduction to linear algebra to the extent of what is required for today's course. Okay, today's lecture. But anyways, I will share this slide to you through Sridhar sir. You can look at it and try to understand and try to derive some of the derivatives of matrices, right? And vectors that I showed. Okay. All right. Now I'm going to begin with regression. Okay, which is my next topic. So in the meanwhile, if you have any doubts, okay, please be free and talk to me. There is no problem. Do you have any concerns or any doubts in whatever has been covered so far? Because I'm going to start with regression right now. So I can give you just 2 minutes so that we can discuss if there are any issues so far. Can I proceed?
Yes, sir.
Hello?
Yes, sir.
Yes, sir. Yes, sir. Proceed, sir.
Can I proceed? Okay.
Yes, sir.
Okay. So now I'm going to cover regression. Okay. And what I'm going to do in regression, I'm rather going to explain to you, first of all, what is regression? Okay. What is overfitting in regression? How do you address overfitting in regression? Okay. And then how to compute the parameters of the regression function. Okay. And to learn the parameters of the regression function, you will use the matrix derivative that I just mentioned to you right now. Okay. That dou by dou x of x transpose mx equal to m plus m transpose x, that formula, and dou by dou x of x transpose y is equal to y. Okay, those two formulas I'll be using. Okay. I was just drinking some water. Okay. Is the slide visible to you, everybody?
Yes, sir.
Yes, sir. Yes,
Okay,
sir.
good. Fine, fine. Okay. See, right now, we will just go through the basics, as I told you, but these basics are very important because even in the later lectures of this workshop and even in the next workshop, they are very important. Okay. So let me start. Okay. I have already shown you this figure, right? I told you that this is a sine wave which is corrupted with noise. Okay. And I want to actually fit a curve to approximate this sine wave. Okay. All right. So in general, the curve that I will fit is a polynomial. Okay. So if it is W0 plus W1x, what is the type of curve? It is a straight line. Okay.
Straight line.
If it is W0 plus W1x plus, straight line. Yeah. W0 plus W1x plus W1x squared, W2x squared. What is it then? It is a, what type of curve is it? Quadratic curve. Correct? Quadratic curve. Then if it is W0 plus W1x plus W2x squared plus W3x cubed, what type of curve is it? It is a cubic curve. Okay. So on. So for any order m, okay, there is a curve yx comma w, which is summation wj x to the power of j is equal to 0 to m. Is it clear to everyone?
Yes, sir.
Is it clear? So
Yes,
what
sir.
I'm going to do is I'm going to give you a set of points and I'm going to fit different polynomials on that. Okay, and then study the behavior. Okay, all right. So this M is called as the order of the curve. Okay, so if M is 1, the curve is linear. If M is 2, the curve is quadratic. If M is 3, the curve is cubic. So essentially the highest order. Okay, the highest order, okay, of the polynomial function. All right. Now, what are the W0 to Wm? They are nothing but the weights. Okay, they are nothing but the parameters, okay, which you have to estimate. Which you have to estimate. Okay. All right. And in general, this function of x need not always be linear. It can also be non-linear, like x squared, x cubed, and so on. Okay. 5x squared, 5x cubed, and so on. Okay. So these are okay. All right. So this is my idea. I'm just expanding on this curve. Okay. So I have a set of points which are marked in blue. Is everybody able to see the slide?
Yes, sir.
Is everybody able to see the slide?
Yes,
Okay.
sir.
Yes,
I
sir.
have a
Yes, sir.
set of points marked in blue. Okay. I have a set of points marked in blue. And then I have a red curve. Are you able to see both? Now this red curve, okay, is the best polynomial fit, okay, of some order m, which I have to estimate. Okay. So the formula is that you have to define. So you see these yellow lines, no, which are going past. These yellow lines. Are you able to see some yellow straight lines? What are they?
No.
They are
Red.
nothing but the deviations. Okay. Huh? What is it? See, you have some yellow line joining the blue point to the red line. Yes or no? Okay.
Yes, sir.
So
Green
it
line.
is nothing but, yeah, green line. Okay, green line. Fine. So what is that? That is nothing but the error. Okay. That is the error. Okay. Or the deviation of the actual sample, which is blue point, from the estimated curve, which is in red. Is it clear to everyone? Is it clear to everyone?
Yes, sir.
Is this clear? Is it clear? Okay? So
Yes, sir.
I have to choose the curve in such. I have to choose the curve in such a way that the sum of these green lines or these deviations should be minimum. Okay? For all the examples, for all the training examples. So that means I will say error EW. W is the weight vector, okay, whose coefficients are W0, W1, W2 to Wm. Okay, that is equal to y xn comma w minus tn squared n equal to 1 to n half. Okay, so this is my error function. Is it okay? Now you please tell me, how many variables does this function have?
Two variables.
Two. Okay, two variables in this example, but in general, m variables. Okay, m variables, w1, w2 to wm. Okay, m variables. Fine. So what I'm interested in, sum of squares of the errors between the predictions, okay, and each data point, okay, with the target value tn. Okay, that's what it is. So targets are the actual values. The predicted values are y xn comma w for the same xn. Okay, so y xn w minus tn squared n equal to 1 to n half. Now this half is used for a particular reason, just to simplify your evaluation when you do derivatives. Okay, all right. So now we have to choose the value of w for which EW is as small as possible. Okay. All right. Is everybody audible? Because there was some sound. That's why I have a doubt. Audible, right?
Yes, sir.
Hello?
Yes,
Okay.
sir. Yes, sir. Audible.
Yes, sir.
All right. All right. Yeah. Okay. So everybody is clear how you got. So this is again, okay, related to empirical risk minimization. Correct? Why am I saying that? You see, n equal to 1 to n. N is nothing but the number of training examples. Okay, the number of training points for which you want to regress upon. Okay, and this is what yxn comma w minus tn is what? It is a loss. Okay, if you're perfectly fitting the curve, or rather, if the curve is passing through all the points, what do you think this error will be? If you have a scenario
0.
where the zero. But that may or may not be achievable, correct? You may not be able to get the minimum value of 0. But at best, what you will do is you will find the parameters w such that this error function is as low as possible. Okay, is as low as possible. So this half summation yxn minus w minus tn whole square is also called as the risk. Okay, risk or loss. Okay, so different in pattern recognition you call it as loss. In neural network you call it as risk. Okay, so that means you want to minimize the risk. Okay, and please remember that this E of W is a function. It's a multi-dimensional function of m variables. Okay. All right. Can I move on to the next slide? Everybody, is it clear? Is this formulation clear to everyone? Okay. So I've explained to you what regression is. I've also given you a idea of how to generate the cost function. This is also called as cost function or loss function or risk function. Okay. All of them mean the same. All right. Okay. So I want to minimize this function. Okay. So that means I want to minimize it with respect to what? W. Okay, and W is a vector, mind you. Okay, W1, W2 to Wm. Okay, all right. So I will have to learn the weights. Okay, W, and this function is anyway quadratic because it has a power of 2. It's a quadratic function. So how will I compute the minimize? So if I give you a function and ask you to minimize it, how will I do it? You guys know how to do it. Tell me. I give you a function f of x. I ask you to minimize that function. How will you do it?
Differentiation.
Differentiation. Now I'm giving you a scalar function. Mind you, I'm giving you a scalar function. Okay, E of W1, W2 to Wm. Okay, I'm asking you to find out its minimum value with respect to the W's. How would I do it?
So we will
Hello?
use iteration method. We will use iteration method.
No. I have already explained to you. If I have a scalar function and if I want to compute its derivative with respect to the parameters, what is it called?
So not be able to understand.
Okay, I'll explain to you. This is E of W. Is this a scalar function or is it a vector function? This one, E of W. Is this right hand side? Is this a
Scalar, sir.
It's a scalar. It's a scalar function. And how many parameters are there in this function? How many weights are there in this function?
One. N number of weights
Not
are
one.
there.
M number of weights.
N
number of
N
weights.
number of weights.
Okay. So you remember what is called gradient, no? We just covered something called gradient. And I said gradient is what? What is gradient?
Gradient is a vector function.
Gradient is a vector, correct? And it is with respect to what? With respect to a scalar function. Okay?
Yes, sir.
All right. So you will use the concept of gradient. Okay. Fine. Anyways, you don't need to worry. We will derive it shortly. But what I'm saying is, you should remember that this error function is not two-dimensional. It is actually multi-dimensional function. Okay, multivariable function of m variables, and you have to take the derivative with respect to each of the variables. Okay, so you go for gradient. Okay, all right. Okay. Are you clear so far, or is there some doubt?
Yes, sir.
I
A
don't
bit
want
of
people to
clear.
get
There is a more
lost
clarity.
somewhere. Okay.
Sir,
There is more clarity now? Okay.
you can rotate your phone
Yes.
so you can rotate your phone so that PPT will clear.
What? I didn't get it. What are you saying?
So I'm saying that you can rotate your phone, then PPT will
Okay.
visible full.
Okay. Okay. Yes, I've rotated. Is it visible now? Better?
Yes, sir.
Okay. Okay. So what I'm saying is the error function is a multivariable function. Okay. Because W is a vector W1, W2, Wm. And if you want to take the derivative of this function, it's called as a gradient. Okay. All right. Now, this order of M, okay, what is the best value of M you will choose? That depends upon your user. Okay. So let me come back to this example of the sinusoid, which is corrupted with some noise. Okay. If I use M equal to 0, M equal to 1, okay, what do you think? Is the fitting good or is it bad? Does the fitting look good or is it bad? Compared to M equal to 3.
Bad.
Huh?
Bad, sir.
No. Is the fitting good or is it bad for M equal to 1 as compared to M equal to 3?
Bad.
Not bad.
Sir, M equals to
Bad, right?
1 is good comparative to 3.
Why?
M equals to 3.
No, M equals to 3 is more better. Sorry.
Error is lesser.
More better.
It has a lesser error.
Yeah. So, right. So this is what is called underfitting. Okay. This is what is called underfitting. Like M
Sir,
equal to
which
0
one?
and M equal to 1. M equal to 0 and M equal to 1, that is a poor representation of the curve because it doesn't follow the sine curve properly. Okay. Whereas M equal to 3 kind of approximates the sine curve. Okay. So the fit is quite good. Let me just expand it. Are you able to see that? M equal to 3,
Yes.
best fit to sine 2 pi x. Okay. M equal to 3 is a good fit as compared to M equal to 0 and M equal to 1. Okay. So M equal to 0 and M equal to 1 poses what is called an underfitting problem. Okay. Now, what about M equal to 9? M equal to 9 is a case where you overfit the data. Okay. Hello?
Okay, sir.
Yeah.
Are you able to hear?
Yes, sir. Yes, sir.
Yeah. M equal to 9 is a case where you're overfitting. You see, overfitting means what? You are plotting a curve which is passing through all the points. So what will be the training error? It will be 0. Okay. What will be the testing error? It's going to be very large because the curve is very, very complicated. Okay. Whereas if you look at M equal to 3, okay, the choice of M equal to 3, which is the model parameter, is quite decent because it kind of approximates the sine curve, and that is what you want. Because you know that the signal that has been generated is nothing but a perturbed sine curve. Okay. So it is better to look for a model which will best fit that curve. Okay. Whereas M equal to 1, M equal to 0, okay, they don't satisfy that because they don't approximate it good. Okay. And likewise, M equal to 9, it is some complex curve very far away from the sine curve. Okay. Is it clear to everyone? So what is the take-home message from here? The take-home message is that the model order is also very important. Okay. You have to choose the value of M correctly. And that is generally done, okay, so that the error, the error okay, E of W function corresponding to a value of M, okay, that is minimum. Okay, all right. Okay, all right. So if you overfit, okay, your training error goes to 0, which is that blue line that you're seeing here, and your testing error will just go very high. Okay, so that is what is illustrated here, and that is at M equal to 9. Okay, but there is one range, let's say between 3 to say 6. Okay, where your training error is low, your testing error is also decently low. Okay, so that your model will get fit properly. Okay, and for values of M which are less than 3, like 0, 1, 2, you see that the training error is high and the testing error is high. Okay, so the model that you choose, okay, should minimize the training error, not necessarily 0. It should also minimize the test error. Okay, that is the goal. Okay, but if you overfit and underfit, okay, if you overfit, your training error will go to 0, but your testing error will go very large. Okay, and if you underfit, both your training and testing error will be large. Okay, is it clear to everyone?
Yes, sir.
Yes, sir.
Hello? Okay, okay.
Yep. Yes.
So that is what I'm talking about, complexity. Okay, so we are going to fit a higher order model, means higher order of M, okay, with limited training examples. Okay, your training examples are limited, then you are making the complex model very complex. Okay, and this leads to the problem of overfitting, and overfitting is nothing but a manifestation of curse of dimensionality. Okay, see, what did I say about curse of dimensionality earlier? If you remember, I told that higher the dimension, okay, higher the number of parameters, the worse the classifier can become. Okay, so that is the same thing here. If you increase the weight vector, okay, that means your model order is increasing, your weight vector is increasing in dimension. Okay, more parameters have to be estimated, your training data is less. Okay, so that leads to overfitting problem or curse of dimensionality. Okay, now the question is, how do you remove this perturbation? How do you eliminate this curse of dimensionality or overfitting? So one thing we can do is increase the size of the training set. Okay, you can increase the size of the training data. All right, the other way is this least squares problem that is there. Now this equation is called least squares. Have you heard of least squares? This is nothing but least squares. Okay, y of xn comma w minus tn whole squared, summation I equal to 1 to n into half. That is called as least squares. Okay, now you add a regularization over here. Okay, lambda by 2 mod w squared. Okay, so that large weights are not favored. Okay, so this is a penalty term, okay, which is also called as regularization. Okay, and this can actually deter, okay, or kind of stop the system from overfitting. Okay, so far so good. You guys are following whatever I said. See, I told you always that whenever a model is overfitting, okay, you will have to do some method to counteract that. Yes or no?
Yes,
Yes.
sir.
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
So I'm giving you two methods. One method is increase the number of training examples, okay, and the other method is you add a regularization term. Okay.
So what is the
So that
regularization?
regularization will help. This constant plus lambda by 2 mod w squared.
Then
This
can you
const-
explain in words? Matlab, what
Okay.
is actually happen when the regularization is done?
Okay. So what is generally happened in the regularization is done is that, see, how many of you know Lagrangian multipliers? Have you heard of Lagrangian optimization?
Yes.
Madam, have you heard of
Yes.
Lagrangian optimization? Okay. So if I say minimize x squared plus y squared, okay. If I say minimize this function, some function, okay, and if it's unconstrained, sometimes what happens is that your minimum value can occur at a very large value of the variable. Okay, like W can be very large. But rather, if I say minimize the cost function, subject it to W transpose W equal to 1. Okay, so that means what? I am minimizing the error function subject to the weight vector being small in magnitude. Okay, so that is what is done over here.
That is regularization. Okay.
Yeah, means I'm searching for a constraint. Okay. Okay.
Okay, sir.
All right. Fine. Let me see where I am. Okay, great. So now let me just okay. Right. Okay. So so as I told you, if you have 9 points and you're fitting a high order polynomial like 9th order, okay, then I told you that you are going to actually overfit, correct? So if you don't use a regularizer, you will get a very complex curve.
Yes, sir.
But if you use a regularizer, then your curve will be less complex. Okay, your curve will become less complex, so that you will not overfit. Is it okay? Okay. All right. Okay, so this slide is just going to give you an idea of regularization on the error. So you will see that both training and testing error, they both are. See what happens in overfitting. Training error goes to 0, but testing error will just go very high. Okay, but when you use regularization, okay, the training error will not go to 0. It will be some minimum value. It will be high, but it's okay. It's at least as good as, it's not as bad as overfitting. Okay, so your training error and testing error both will be relatively a little bit higher. Okay, but it is still tolerable. Okay, meaning you're not overfitting the data. Okay, your test accuracy would have come down by then. Are you able to see that?
Yes, sir.
Okay, so if you are overfitting, what will happen is the training error will go to 0 and test error will go very high. Okay, but if you do regularization and if you reduce the overfitting, your training error will no longer be 0. It will be higher than 0, but your testing error would have come down. Okay, and finally at the end of the day, right, you want the regularize, you want to actually do a good job, right, while at the same time, just ensure that your regression is doing good. Okay, you just want to do a good job at the end of the day. Okay, like your testing error should not go very large. Okay, because see, finally at the end of the day, right, your performance, your algorithm, everything would relies on how much your testing error is. Okay, so your testing error you cannot afford to have a testing error which is very large. Okay, so if you do regularization, you will avoid the testing error from going very large. So your testing error will be tolerable. Your training error will also be tolerable, not 0. Okay. All right. Okay. All right. I also want to talk to you about what is called as validation. Okay. Somebody asked me the doubt on validation. Is he around right now? In the last lecture, in the morning lecture, somebody asked me about validation. So I want to just give an idea. So who asked me a question on validation in the morning? Is he around? Okay, anyways, I'll continue. Are you all able to hear what I'm speaking?
Yeah, sir. Yeah, sir. It's audible, sir.
Hello?
Yes, sir.
Yeah, it's
Yes.
audible.
Okay. Yeah. No, if you are silent, then I get scared, actually. Okay, fine. Okay, so I want to talk to you something about validation right now. Okay, see, I want to talk to you about a company, about how they develop products, and just give you an idea and then relate it to this. Okay. Of course, I'm not a software engineer, so I'm just making a general statement here. Okay, it's not pertaining to any. So when a company wants to release a product outside, okay, in general, I'm talking about, they talk about different versions, no, alpha version, beta version. There's a lot of internal testing that happens within the company. Okay. And once they release the product, it should be free of any defects. You all agree or not?
Yes.
That internal testing happens within a company. People who are in software can definitely relate to it. But you will not release a product outside unless it has been super tested properly with all the things being addressed. Okay. So in a way, what actually happens is that a validation is kind of done about the effectiveness of your system. Now, in a similar example, what is done over here in pattern recognition in artificial intelligence systems is that when you're doing when you're developing an algorithm, okay, generally the training data only will be given to you. Okay, you understand? Because testing data is generally unknown. Okay, you have to decide on the label of the data, or you have to decide on what it's the value it should regress onto. Okay, so so what is done is, let us say you have 1,000 training samples available to you. You actually train on, say, 800 samples and test on the balance 200 samples. Okay, on training samples itself. Okay, and so you will randomly choose 800 samples and test on the remaining 200 samples. And each time you will randomly choose some subset of samples for training, and the remaining part of the training you will reserve for testing. That is what is called validation. Is it clear to everyone? Any doubts? Hello?
No, it's clear.
Hello,
No,
are you
sir,
able
no,
to
sir.
understand? Able to hear?
Yes, sir.
Yeah,
It's
it's
clear.
clear.
Huh?
It's clear.
Okay, so that means you're doing internally, you are validating your approach. Okay, so you should always not touch the test data. Okay, you understand now what I'm saying? The test data is the data that the algorithm has to be tested to see how good it is. Okay, it should never be tampered. Okay, meaning that you should never train on the test data. Okay, so if you want to improve the parameters of your model, or you want to check your model how well it works, okay, you do a validation, so that once you do a validation, okay, you can actually see. Okay, so the idea is this: like in case of regression, no, you will have the training data, you will split the training data into training and validation. Okay, and
Hello, sir.
you will evaluate the performance for different values of the model parameters M. Okay, M equal to 0, 1, 2, 3, and so on. Okay, and you will see the training error and the validation error. Okay, and of course you will be doing regularization and all that if required. Okay, and the model that gives the model order, or the order of the model, the value of M, that gives the minimum value of the error function. Okay, during valid or the validation set. Okay, that will be used for testing. Is it clear to everyone?
Yes.
Okay, so what we do is we reserve a part of the training data. Okay, we reserve a part of the training data for testing. Okay, or for validating the performance of the algorithm. Okay, so this is the idea of validation, and validation is very, very important, because whatever algorithm, okay, you actually develop, okay, you need to validate it, okay, so that you can learn the parameters well. Okay, all right. So
Hello, sir.
can I proceed? Okay.
Hello,
So
sir.
what is done here is the following, that, yes, any doubts?
Sir, can you hear me?
Okay.
Hello.
What is done here? Somebody is talking something. Please tell me if you have any doubts.
Hello.
Okay. So, yeah. Hello.
Sir, can you hear me? Hello.
Yeah. Tell me.
Sir, can you please tell me about the thing which you said, training validation, once more, because it's not clear for me. Hello.
What are you asking? Can you just, your voice is very feeble.
Can you please tell me again about the training and validation shortly?
Okay. 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 So, what is your name? Can I know
Rajesh.
your name?
Yeah, my
Okay, Rajesh.
morning I have talked to you regarding that X-ray image, right?
Yeah.
Can you could please explain? Actually, I have doubt in training how to actually I have having 1,000 samples. You said about you will take 800 for training, 200 for testing. Hello.
Yeah.
Can
Tell me.
you-
Yes. Tell me.
Yeah. How to identify how if I have all the normal chest X-ray images.
It is random. It is random. It is random. Means you can take any 800 samples for training and 200 samples for testing.
Okay. When I go for example, when I go for this training should be comes under neural network. How can I apply for that? Whether I can.
So see, generally what happens is that you have training data, okay. Generally they also do something called as k-fold validation. So that means what you do is you divide the data into k chunks of data, okay, sub-data, and you train k minus 1 and reserve k for testing, the kth one for testing, and you keep repeating it. So supposing I want to do three-fold validation, okay. I will. Rajesh, are you able to hear what I'm speaking?
Yes, sir. I am here.
Okay. No, because see, there is some cross disturbance. Please unmute because otherwise your voice is feeble, and that's the thing. Okay. So what I'm telling you is that if you have three-fold validation, okay, you will divide the training set into 3 parts.
Okay.
Okay. And you will select the first one for training, second and third for testing. First 2 for training and the third one for testing. Similarly, you will select the first and third for training, set the second one for testing. Okay. So like that, how many combinations you will have? You will have 3 such combinations.
Yes, sir.
Okay.
Yes.
So that means you take k minus 2 parts you choose for training, 1 part you use for testing.
Okay.
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 So you'll have 3 rounds. No.
Yeah.
So you'll run the neural network. You will get 3 performances. Okay. You will see which performance is the best amongst the 3. Okay. And then you retrain the full network using all the training samples with those parameters.
Okay, sir. Thank you.
Is it clear?
Yes, sir. Yes.
Okay. Any more doubts? Okay, good. So we are having good progress. I can see that. Okay. So that's what I was talking about, validation. So I'll move ahead. Okay. All right. Now, we have another 1 hour left, actually. So I would like to just give you a very rough idea about how this weights are learned in terms of regression. Okay. So please try to follow it. But if you have understood so far, I'm at least very happy that whatever I have taught, okay, if you're able to understand and if you've taken steps, it's a stepping stone. Okay. But now I want to derive, for sake of completion, okay, the weight vector. Okay, like how you compute those W's, W1, W2 to Wn. Okay. So I'll try to explain it. Okay. If something is not clear, it's pretty okay, because it all depends on how much of mathematics you people are inclined to, because different people are from different streams, I can see. But at least the essence is that, those derivatives, which I discussed at the beginning of the class, right? The gradient and so on. I will give you an illustration of how it is used to compute the derivatives here, okay, to get the minimum value, okay? So can I please move ahead? Any doubts so far? Because the next few slides will go a little bit faster, so that I'll just give you a fair idea how to work it out. And people who are interested should definitely go back and work it out, okay? Since I'll be sending the slides, it should not be a problem.
Hello, sir.
Okay? Yes?
One more note I have. Can I ask a question?
Yeah, please ask.
Can you suggest me some of the algorithms which can follow for this training, testing, everything? What are all algorithms like for classification?
Yeah, so we will study this Bayesian classifier very soon. No, in about 10 minutes we'll start that. Then your question will be resolved. Okay?
Okay.
Okay. Okay. So I'm going to quickly go through these slides, okay? Because see, in a general classroom, I would have definitely derived it on the board, okay, and explained it. But since now we have little bit of lagging behind time, so I've explained you the concept and the idea behind it. So now it's just the math. So please try to follow, okay? All right. So you are given n training examples, okay, with scalar target values x1, t1, x2, t2 till xn, tn, okay? And I'm defining some basis functions, okay? Phi x1, phi of 1 of x, phi 2 of x, phi m of x, okay? So, for example, in the polynomial case, okay, what will be the basis functions in the polynomial case? If it's m order polynomial, it will be 1, x, x squared, x cube, and so on. Is it okay? Is everybody clear? Hello?
Yes, sir. Yes, sir.
Okay, okay. So they're all non-linear, okay? So that means for a polynomial fit, phi of x is 1, x to the power of xm, okay? All right, now let me move on to the next one. Okay, so what we do here is that you'll define a vector of weights, then a vector of predicted values, okay, a vector of target values, okay? So we will check the dimensions appropriately, and we will write every phi 1, each of the predicted values, we'll write it as phi transpose of x1 times w, okay? And we will write this in this form, okay? And then we will write this as y is equal to phi times w, where phi is a matrix and w is a vector, y is a vector, okay? And finally, you will write the error function as half summation ti minus y squared. This is okay, no? This part is clear. This is nothing but the empirical risk minimization part, okay? You write it as t minus phi w transpose t minus phi w, okay? All right?
Okay.
Can I proceed?
Yes.
Yes? Yeah, hello, can I proceed?
Yes, sir.
Yes, sir. Yes.
Yes,
Okay. So I would suggest you to go back and try to go through these equations slowly, okay? Because they are very important, okay? And if you have understood this very well, okay, ti minus yi, you are just writing yi as, okay, phi I transpose w, okay, and then you are writing it phi y as phi w, okay? All right, fine. So I come here, okay? I come here. Now my error is a function of w, is a vector half summation I equal to 1 to n ti minus yi whole squared, okay? This is half t vector minus phi w. Phi is a matrix, please remember. Phi is this matrix, okay? Then phi w transpose t minus phi w, okay? Now, what I will do here is I will multiply this as t minus phi transpose w, t minus t minus, okay, I'll just multiply this t and then phi w, okay, and then I will put this t inside and get this expression, okay. All right. And then I'll do some tricks of linear algebra and write this, okay. You can please verify it, okay, no problem. Okay. I want to minimize this function. What do you think I will do? I want to minimize this function. So what do you think I should do? Anybody, quickly. And this function is a scalar function. And it's a scalar function with w, I mean, it's a scalar function with m independent variables. So if I want to find out those m independent variables and that minimize this function, what operation I should do?
Differentiate until 0.
Differentiate or rather gradient. Remember, it's gradient.
Gradient.
Okay. Gradient. Okay. So I will do the gradient, dou E by dou W. Okay. And this is where I will use, okay, the properties of the vector derivatives. Remember, like dou by dou x of x transpose y is a y. Okay, dou by dou x of x transpose mx is m plus m transpose x. Remember that we just covered it in the beginning of the lecture. Okay, I will use those properties. Okay, and then take the derivative, set it equal to 0. Okay, so that gives me phi transpose t minus phi transpose phi w star equal to 0, and w star is phi transpose phi inverse phi transpose t. Okay, so this is my optimal weight vector, okay, for a given order m that will minimize the error function. Okay, is it clear to everyone? At least the idea. I've not derived it. The derivation is quite straightforward. I'm sharing the slides as soon after the lecture is over. Okay, probably after the workshop you'll get an access of these slides, so you can just go through if you're mathematically inclined to do this derivation. Okay. All right. Okay. Now the last part is the regularization part. As I said, we'll add this plus constant lambda by 2 w transpose w and repeat the same thing. And what you will see is that there will be a plus lambda I, where I is the identity matrix that comes in. Okay, over here. All right. This is another part for people who are interested. So far, we just implemented for one dimension. Okay, but in general, you can have multiple dimensions also. Okay, so that is what is this. All right, so we will just skip that for the time being. So whatever I covered is sufficient for regression as far as your course is concerned. Okay, and for people who are interested for reading the material, okay, these are the sections of reading from pattern recognition, machine learning, Christopher Bishop. So you can read sections 1.1, 1.3, 1.4, and 3.1. Okay. So the content of this lecture has been taken from there. In fact, I think Dr. Sridhar was suggesting me to add this up. So I've added it in this lecture. Okay. So the content for reading, like meaning the content for reading means the ones which I've taught. Okay. They all can be seen in this book in these relevant sections. Okay. 1.1, 1.3, 1.4, and 3.1. Okay. And regarding the earlier talk on classifiers and so on, okay, you can do the heart chapter 1 and 2. Chapter 1, okay, chapter 1. Okay. So we are ending on regression right now. So do you have any doubts on regression, which we can? So this logistic regression is another topic, but the logistic function we need to introduce. Okay, so probably we will introduce it in the neural network session because logistic functions are generally used there. Okay, So whenever we cover neural networks, right, then the logistic regression would play a role. So we will cover logistic regression there. Okay. But this is the basics of regression as far as the course is concerned. Okay. Any doubts so far before we move to Bayesian decision theory? Hello?
No, sir. Please proceed.
No, sir.
Sir, please go ahead.
No
sir.
doubts? Yeah,
No
yeah.
doubt, sir, till now.
Fine. Okay. So we have another 40 minutes. Okay. So I will also start covering the Bayesian decision making. Okay. Okay. So all right. So in this Bayesian decision making, we are going to rely on generative classifiers. Okay. What are generative classifiers, if you recall? I told you generative classifiers make use of distribution of the data. Okay. Distribution of the training data. Okay. So we are going to go back to generative classifiers. And from that perspective, we are going to talk about Bayesian decision theory. How many of you are familiar with the Bayes rule? Participants, I'm asking you a question. How many of you are familiar with the Bayes rule? You probably would have, I hope all of you are in the engineering background. So you would have come across Bayes rule, right? In probability? Yes or no?
Yes.
Sir.
Yes, sir.
Yes,
Yeah?
sir.
Yes, sir.
Okay. So this Bayes rule is going to be used, okay, in developing this classifier. Okay. So that's the number one thing you need to know. Okay. All right. Okay. So one thing you should remember here is that the classification is different from regression. Okay, in the sense that the output will be a discrete label denoting the entity of the class. Correct? No, because the labels have to be given to the classes, because we are talking about supervised learning over here. Okay. All right. And the Bayes rule is very powerful. Okay. And the knowledge of it is the Bayes theorem, sorry, is going to use to develop the classifier. Okay. With appropriate decision surfaces. Okay. So it's a generative model, and it is going to be optimal if the distribution. Yeah. Any questions? Hello? Yeah. It is going to be the optimal model if the distributions are known. Okay. And it's going to follow the supervised learning paradigm. Okay. Okay. Let me go back to the sea bass and salmon. Okay. Example. Okay. And the problem, as you say, was to recognize the types of fish. And the category was a 2-class category problem. Okay. Okay, let me change this example a bit and then come back to sea bass and salmon. Okay. Okay. So, okay, I want to ask you a simple question. Okay, to everybody. Common sense. Okay. Please listen to me carefully. Okay. I'm just changing the domain of the problem a bit for your understanding. Then I'll come to sea bass and salmon. Okay. I want to identify between oranges and apples. Are you able to hear what I said?
Yes.
I want to identify or classify between oranges and apples. Okay? Orange is a fruit, apple is a fruit. I want to classify oranges from apples. Okay? That means given a fruit, I want to check whether it is an orange or whether it is an apple. Okay? Is everybody clear?
Yes, sir.
Is everybody clear? Okay.
Yes.
Now, I'm making a statement saying that, okay, I had a box of fruits given to me. In that, I found 80% of oranges, 20% of apples. Okay.
Yes, sir.
I had a box of fruits. Okay. 80% was oranges, 20% was apples. And I go and say, okay, look, I will choose the unknown fruit as oranges because I saw more oranges. Okay.
Okay.
Do you think that decision making is correct? I'll repeat it again.
No, sir. I think
I have-
apple. We should choose the apple rather than orange.
No. Let me repeat. Madam, just 1 minute. Let me think and tell me. Just think and tell me. Okay. I have given you a box of fruits. In that, you found 80% were oranges, 20% were apples. Okay. And I'm saying that whatever fruit comes in, like if I give you a fruit, you will say that it's an orange because 80% of the time it was an orange. Okay.
Okay.
What do you think will happen?
The probability of error might increase if apples are going to come.
Yeah. So yeah, correct. So that means what? That means you're right, but
20% of the time it failed.
No. Your decision is it's an orange because I saw oranges more.
Yes, sir. It will
Yes.
produce more accurate result.
No. What will it predict? What will it predict from the? See, I'm giving you a fruit. Okay, you're telling me it is an orange because I saw oranges more.
Yes,
So
sir.
every fruit, you're going to recognize it is an orange.
Yes, sir.
Are you able to see something wrong there?
Yes, sir. Because the data is not, it's not in a correct format. Because we see only a kind of fruit which is having more 80%, right? Whatever the fruit it comes, or if it is other thing, it says it might say no or deny it,
Yes.
or stating it
So
as an
something is wrong.
orange. Yeah.
Something is wrong. Something is wrong. You could guess that, no?
Yes.
Okay.
Yes, sir.
Now, this fact of saying oranges I saw more than apples is what is called as prior information. Okay? Prior.
Okay.
Prior. Prior. Something is
Prior.
So it is like saying, okay, I don't want to be gender biased here, but it's a known fact that girls study better than boys, right? Is it true? I don't know. Madam can say probably, right? You already see, right? In exams, board exams, okay? Girls outshine boys, okay? Now that is the prior. It has happened over many years. You understand? Okay. So now it doesn't mean that the other gender is no better or worse. Okay. So we cannot make a decision based on the prior alone.
Prior messages.
Yeah. Okay. No, wait. I'm just explaining something. Then we will share the slide. Okay. Fine.
Okay, sir.
Is it clear? Okay.
Yes, sir.
Now I want to ask you, supposing I make use of the information that an apple is red in color, orange is orange in color, okay, and then apple is looking like a heart shape, whereas orange looks like circular, okay. Then apple has an orange tinge. Orange has an orangish tinge. Apple has a reddish tinge, okay, something like that. And then if I incorporate that information, do you think I will do better?
Yes, sir.
Yes. Now, correct? Yeah? Everybody
sir.
agree?
Agree.
Right.
Yes, sir.
So what are those? When I say an apple is red in color, orange is not so red. Orange is round in color. Round in shape. Apple is heart in shape. What do I mean? What are those? They are nothing but attributes describing the fruit.
Attribute. More labels are added in the data.
Not labels, attributes, features.
Okay. Features.
Features. Okay. So if you rely on features, okay, and rely on prior information, okay, then you can develop a good classifier. Good classifier means a reasonably good classifier, so that your decision is not getting biased only by the priors. Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. Clear. So now I'll share the slide. Okay. So regarding this apples and oranges, I just gave it for easy explanation. Okay. Because it's something realistic which you can denote. But in the textbook of Duda Hart, they talk about salmon and sea bass. Okay. So I'm just taking the same example here, but the idea is similar. Okay. So what it means is that now if you decide that the salmon occurs more than sea bass, and you're going to select the salmon because it occurred more, like what you rightly pointed out, all the classifications will go to salmon. Okay. And sea bass will never get identified. Okay. Or rather, like what somebody told me, that, not seeing apples or will push the error rate high. This is also correct. Okay. Fine. So this is what it is. So for example, out of 8,000 fish, let us say 6,000 were salmon and 2,000 were sea bass. So that means 75%, 0.75 is the probability of omega-1, which is probability of salmon, and omega-2 is the class for sea bass. So 0.25. Okay. See, omega-1 and omega-2 are nothing but two variables to denote the classes. Okay. Right. So omega-1 will represent sea bass, salmon. Omega-2 will represent sea bass. Okay. It can be either way also, but whatever, this is some label that you're giving as a notation. Okay, fine. Okay, now what do we have? What I'm trying to say is that you choose omega-1 if probability of omega-1 is greater than probability of omega-2. Okay, so that means to say that always omega-1 will be chosen. Okay, so that is what it is. Okay, you choose unknown fish as omega-1 if probability of omega-1 is greater than omega-2, else the sea bass. So this problem is going to be a big problem because only one decision will be favored. Okay. So rather, the decision rule is going to be flawed. So the salmon will always be favored. Okay, and it is not going to work in practice. So if you just rely only on the prior information, okay, you're not going to make a good decision. Is it okay? Is it clear to everyone?
Yes, sir.
This example?
Yes, sir.
Yes, sir.
Okay. Fine. So now you look for features. Okay. So you look for additional information to describe the sea bass and salmon. So you look for discriminative features. Okay. So the features that you can look are like length, width, color, span, texture, okay, and so on. Okay. Now you assume that there are D features. Okay. So these D features can be stacked by a T-dimensional feature vector for representation. Okay. That is X. Okay. We are just reviewing through whatever you have done in the morning class. Same thing we are repeating because concepts are similar. Okay. All right. Now, I want to just introduce to you what is called as class conditional density. It will become much clearer now than in the morning. Okay. I talked about generative classifiers, right? What did I say is generative classifier? Quickly. What is generative classifier? Anybody? If you recall. Okay, generative classifier means that the data, okay, comes from a distribution, okay, comes from a PDF, okay. So it is like saying that the length or the width of the samples of sea bass, they follow a Gaussian distribution, okay. The length and the width of salmon, they follow a Gaussian distribution of some mean and variance. Okay, or some other mean and variance for the other one. Okay, so you will have a density which is specific to a class. Are you understanding what I'm saying?
Yes, sir.
Okay, I'll give you a simple example. Okay, let us talk about again, gender itself. Okay, let us talk about height. Okay, heights. Okay, height of the population. Okay, so let us talk about Indian men and Indian women. Okay, I can probably say that through experience or through statistics, okay, the height of the Indian man is say 5'6", okay, on an average with a standard deviation of something, okay, and the height of a Indian woman is say 5'4", okay, with some standard deviation. Do you understand what I'm saying? Okay,
Yes, sir.
so when I'm actually doing
Sir,
that statistics,
excuse me, sir. Sir, screen has gone off, sir. Could you kindly check out?
Yeah, that's fine. I'm just explaining something, sir, about just making it easier
Okay,
for them.
right,
Yeah, and then I'll go back. So let me come back to this. Where was I? Yeah. So what I was saying is that I'm measuring the heights of genders, okay, and I am saying that the height of the Indian gent or a man is 5'6" with some standard deviation, and the height of the Indian lady is some 5'3" or 5'4" with some standard deviation. Okay, right? Now, when I actually did the statistics, what is I assumed some distribution for the men and a distribution for the women. Yes or no?
Yes, sir.
Okay, so that is what is called class conditional density.
Okay, sir.
Okay, because there are two classes. One is male, other one is female, and I'm defining the height as a feature, and I'm describing the height by a distribution. Okay, do you understand? Yes, okay,
yes, sir.
So this is what is the class conditional density. So now coming back to the slide again. Okay, so what does class conditional density mean? For every class or category of which you associate the D features to come from a distribution function, and it is class conditional density, meaning for salmon there is a PDF, for sea bass there is a PDF. Okay, and the features are continuous because whatever you're measuring are continuous features like length, width, height, and so on. Okay, and the distribution is no longer single distribution, it is a d-dimensional distribution. Okay, so that you don't need to worry. All right, now I want to cover the Bayes rule, decision theory. Okay, Bayes decision theory. So for the time being, let us work to improve the decision process by incorporating a single feature. Okay, means scalar feature. Okay, and later we'll extend it to multiple dimensions, okay, and for classes greater than 2. Okay, so all right, this is what is the class conditional density. Okay, how many classes are there? How many classes are there?
2 classes.
2 classes.
Yeah,
and
W1,
what
W2.
Is the distribution? They are class conditional. They are class conditional. Okay, so there is a distribution for omega 1. There is a distribution for omega 2. Is it clear to everyone?
Yes, sir.
Yes.
Okay. All right. So this is your well-known Bayes theorem. Have you seen this somewhere?
Yes, sir.
In probability?
Yes, sir.
P of x given omega I, probability of omega I by probability of x. The probability of x is summation. P of x given omega I, probability of omega I. 2 classes I equal to 1 to 2. Okay. So there's a prior term and this class conditional density. Okay. If you pick a value of the class conditional density for a given x, okay, that is called as likelihood. Okay, so likelihood into prior, okay, will give you the posterior probability. Okay, is it okay?
So what is posterior?
Okay, I'll explain to you. See, prior is without any features, probability of omega I, probability of omega 1, probability of omega 2. Okay, so
Okay.
And what is posterior probability? Probability of omega 1 conditioned on x. X is the feature.
Okay, sir.
Okay. So it is like this. Probability of a fruit being orange, given that it is heart shaped. Okay. Probability of getting a fruit being apple, given that it is a heart shape. You understand? That is definitely different from probability of orange, probability of apple. Okay. So the reason is that your features are getting incorporated. Correct? Your features are getting incorporated via the class conditional density. So the prior gets converted to posterior. Okay. Is it clear to everyone? Okay.
Yes, sir.
Okay. Fine. Okay. So this will be the plot of the posterior probability. Okay, for omega 1 and omega 2 separately. Okay. Now, can somebody tell me, okay, what should be the decision in this case? See, earlier you told that you choose that to make the decision depending on which prior is larger. Now, how do you think I'll revise the decision given that posteriors are available? Can anybody tell me? Means I will get a probability of omega 1 conditioned x. I will get a probability of omega 2 conditioned x. Okay, I will get two probabilities. So which do you think I will choose as my correct class?
Probability of omega 1 by x.
Okay, that is, if it is larger, you classify it as what?
Not getting, sir.
Okay, fine, no problem. At least you attempted, it's good. Okay, let me show you this plot. Okay. You take a value of 13. Take this value of 13. Okay. Probability of omega 1 given x is this plot, this number. Probability of omega 2 given x is this number on the y-axis. Okay. Which class will you identify it to be? For a given feature x, which class will it be more likely? Omega 1 or omega 2?
Omega 1, sir.
Omega 1. Omega 1. Why? Why omega 1? Very good. Why? Because probability of omega 1 given x is greater than probability of omega 2 given x. Higher. Correct. So you will choose the class that gives the maximum posterior value. Okay. That's the principle.
Okay.
Is it okay?
Yes, sir.
Okay.
Yes, sir.
All right. So you will choose the class which is the maximum posterior value. Okay. So that's the idea here. Okay. So what we will, so this is the simple Bayesian decision theory. Okay. Wherein you have the priors, you have the class conditional densities. The value of the class conditional density at the given value of x is called a likelihood. You will multiply the prior with the multiplied with the likelihood, and then with a proportional factor or evidence, you will get the posterior. And the decision that you will make is the following. If P of omega 1 given x is greater than P of omega 2 given x, okay, you'll define it to be omega 1. And if P of omega 1 given x is less than P of omega 2 given x, okay, you will base the decision to omega 2. Okay. All right. So now, so there is always a possibility that errors can happen. Yes or no?
Yes, sir.
Correct. There can always be a possibility that you may have an orange that can get classified as an apple. You can have an apple that gets misclassified as an orange. Okay, it can happen. Okay,
Yes, sir.
you understand, right? What I'm saying. A more practical situation, I will tell you. Okay, there is always a possibility that a person who's diseased, okay, may be identified as being healthy by the system, and a person who's being healthy can be declared as diseased by a system. Okay, so that means errors do happen. Okay, so obviously the errors that you have that happen, their probability should be as low as possible. Okay, because that is important, because you cannot tolerate you cannot tolerate the system that has a very high error rate. Okay, so there is always going to be an error which will be associated to the pattern recognition system. So that error will be probability of error given x is probability of omega given x if we choose omega 2. Okay, and probability of error given x is probability of omega 2 given x if we decide omega 1. See, probability of correct decision, okay, and probability of wrong decision, they both should sum up to 1. Yes or no? Because after all, probability is a number that sums to 1. Yes or no?
Yes, yes.
Yes, sir.
Yes, sir.
Is it clear?
Yes,
Okay.
sir.
So probability of error will be 1 minus probability of correct decision. So if your correct decision is high, your probability of error will be low. Okay,
Low, obviously.
given x. Okay, fine. So your goal is to minimize the probability of error, or rather, you will have to maximize the posterior probability. See, only if you choose the class that gives the maximum posterior probability, then only you can minimize the probability of error. Okay, so that is what it is. Okay, so the probability of error is probability of error comma x dx. Okay, which is the marginalization. This is probability of error given x p of x dx minus infinity to infinity. Okay, so that means you want this probability conditional error, probability of error given x to be small for every possible x, for every x. Okay, and by choosing the posterior probability, the Bayes theorem strives to achieve that. Okay, strives to achieve that. All right. Okay. The last part, okay, before I wind up, okay, is that you're going to extend this principle to C classes, and no longer is the dimension 1. It's no longer a scalar feature, it is the dimension, so that I can rewrite the same thing as probability of omega j given x vector, probability of x vector given omega j, probability of omega j into divided by probability of x. Okay, and I will get, how many posterior probabilities will I get? C. Okay, probability of omega 1 given x, probability of omega 2 given x, probability of omega 3 given x, so on to probability of omega c given x. Okay, and I will have to choose that class that gives the maximum posterior probability. Okay, so that's the idea. And also remember, this probability of x given omega j, okay, will no longer be a single dimension random variable distribution. It will be a distribution in multiple dimension, especially in d dimensions. Okay, all right. So that's what I'm saying. The assigned class will be argument max probability of omega j given x vector over all j. Okay, so argument means the index. Okay, index of the class that gives the maximum posterior probability. Okay, and this denominator term, this p of x, okay, summation j equal to 1 to c, because you're having c classes, p of x given omega j, probability of omega j is also called as the evidence. Okay, and is used as a normalization factor, because this p of x is same for all the classes. Okay, it's a normalization factor. So if you just consider the prior and the likelihood and multiply, okay, you will get a factor proportional to the posterior probability. So that itself can be used for decision making. Okay, all right. So I think I'm almost done for the lecture today. Okay, so I just wanted to wind up by a small discussion of how to build a Bayesian classifier. The reason why I didn't want to do too much of math is because there are too many participants, and the participants are from varied areas of research, right? So I'm not very comfortable whether you know about multidimensional Gaussian and so on, okay? Because generally, when this course is taught for undergrad students in IIT, in my institute, they already have a basics of probability, working knowledge of that, random variables, and so on. Okay, so I generally go through a lot of math over there, but the basic idea is what is important, okay, which I've covered. So I would like to just briefly discuss as a small discussion itself how we develop a classifier. Okay, I will just talk about how to recognize, how to classify the 26 digits of the alphabet. Okay, I will just explain that, and then we can wind up. Before that, you have any doubts on Bayesian decision theories so far? I'm done with my slides. So do you have any doubts on Bayesian decision theory which you want to ask before I tell you how to develop a classifier? Because we have another 10 minutes left. So that's the reason I just want to ask you if you have any doubts left, any doubts to discuss. Hello? Am I audible?
Yes, sir. I'm just looking at whether any hand raise are there.
Yeah. Because see, I'm done with the slides for today. Okay. So I just want to end up by just telling you how to design a classifier just as a description. Okay. So that people who are interested can pursue it further. Okay. So this is a very basic course which I have covered, but it's very important because a lot of things are covered. Okay. So that you can go back and have to get into the field. Okay. So any hands were raised, Dr. Sridhar?
Sir. Hello, sir.
Yeah.
Sir, I guess there are no doubts. I'm just talking to participants. If you have any doubts, kindly interact with sir. Sir is having around. Sir is open for discussion for 5 to 10 minutes. So if you're having any discussions, any ideas related to your research works, kindly interact with sir. Answer, sir.
Sir, I'm available, sir. Please tell me.
Yes, tell me.
Sir, I guess there are no doubts.
The doubt.
Okay. So I would like to just wind up now in 5-10 minutes. I just want to tell the students, participants, how to build a pattern recognition system. As I said, I'm not sure about your background, so that's the reason why I didn't cover it intensively. I've given the basic idea. Okay. Any classifier in generative classifier to generate the class conditional density. Okay. Actually, assume a class conditional density, estimate the parameters of that. So I'll give you an example. See, when I made a height of feet and 3 inches with something. So how did I get that 5 feet and 3 inches? How did I get the standard deviation? I got it from estimating training data. Okay. So for that, map estimation. Okay. Many methods are there. Okay. Tomorrow, I think you're going to have a class on GMM, right? If I remember, Gaussian mixture modeling.
Yes, sir.
Okay.
Morning,
They're
sir.
all used over there. Okay. Huh? Hello? First, let me just finish and then you can ask your doubt. Okay. Anjirati?
So there is one hand raise, sir.
Hello?
Hello.
Hello, sir.
Yeah, sir. Let me finish, sir, and then I will come back to his doubt. Caesar, sir.
Yeah, sir.
Hello.
Yes, sir.
Hello.
Yes, sir. Please go ahead, sir.
Hello?
Please go ahead, sir.
Yeah, let me finish explaining, and then I will come back.
Okay, sir.
Yeah.
Okay, sir.
So what you have some estimation techniques. Okay, you have some estimation techniques like maximum likelihood, map estimation, okay, Bayesian estimation, and so on to estimate the parameters. Okay, and that is one thing you have to remember. Once you have class conditional density, your prior should be given to you. Okay, either it is given to you frequentist approach or whether you have to estimate the priors. Okay, once you have the prior and the class conditional density, from the class conditional density you can describe what is called as the likelihood, okay, of that feature vector occurring. Okay, and then you can multiply both proportionality, they'll be proportional to the posterior probability. Okay, and then you find out which class is the maximum posterior. Is it okay? So we'll just go back to 26 alphabets in the English language. So there are 26 classes. Okay, you derive some features. Okay, you derive some features. Okay, you assume estimate the parameters, variance or mean and what is called covariance if there are multiple features. Okay, by maximum likelihood. Similarly, you do the same thing for samples of class B. Similarly, given a test data, okay, you just find out the multiply with the respective priors, okay, which is also given to you. Which class of which alphabet gave the maximum positive assigned to that. That's all. Okay, so that's the basic idea of the Bayesian classification framework. Okay. Yes. Okay, so I think I'm done with the explanation. So Anchi Reddy can ask the question.
Yes, sir. Yes, sir. Sir, good evening, sir. My name is Anji Reddy. Sir, regarding feature selection, is there any constraint about number of feature selection for that experimentation?
So there are many methods. So for example, you can, you do dimension reduction, you set the number of dimensions, you need dimensions reduction. So how many relevant features I want? 10, 20, 30, that is set by you. Okay.
Is it good?
And sometimes there are some algorithms called as forward.
Is it good to take?
What is it?
Is it good to take high number of features?
See, it all depends. If you take very high number of features, I told you, the curse of dimensionality will come in. I was talking to you, something called overfitting, curse of dimensionality issues can turn up. Okay, some of the features will be redundant because they will be dependent. So the idea is to take features which are independent, less correlated to each other. That's the key. So if you have it is a classifier is happy, okay, sometimes, especially because in generative classifiers, the more the dimension you increase, your common vector, covariance matrix, and things like that you want to estimate will go up high. Okay, which I didn't issue is there. But in terms of neural networks, generally there are methods to overcome this overfitting problem, so that like dropout and regularization, which I was talking to you about. So there are ways to counteract that. I would suggest that better work with some optimal set of features, which is good for discrimination, rather than going.
Yes, sir. Yes, sir.
Very high.
Thank you, sir.
Is it clear? Any more doubts? Okay, so I think.
Sir. Yeah, sir. I guess there are no more doubts.
Wind up. Okay.
Oh. Hello, sir. Hello?
Yeah.
Yes, sir, I guess there are no more doubts from the. I guess there are no more doubts from the participants. And my sincere request to all the participants, as sir has already given his contact mail ID today morning. We are going to share the same mail ID to all of you. So if at all at any point of time, if you want to interact, you can interact with sir. And sir, on behalf of Lendi Institute of Engineering and Technology, I convey my sincere thanks to you, sir, for having spared your valuable time to enlighten all of us. Thank you very much, sir.
Thank you. Yeah. Thank you.
Thank you, sir. And my sincere request to the participants, tomorrow we are having 3 sessions. I'm sorry, the schedule was a little bit tight tomorrow, because the idea of keeping this many number of sessions tomorrow is, I don't want you to miss any of the basic fundamental concepts that are really essential for you to work on machine learning in the forthcoming future. So that is the reason why I have incorporated around 3 sessions today, because I strongly felt like if you miss some of these fundamental sessions, it would be of a great loss to all of you, especially those who are planning to pursue their research work in using machine learning or deep learning algorithms and applications. So tomorrow morning, the first session is going to be taken by Dr. K.T. Deepak. He's assistant professor at IIIT Dharwad. Sir is going to address on hidden Markov model and GMM. Sir is going to address us from 10 to 11:20 or so, followed by we have Dr. K. Srinivas, assistant professor NIT Warangal. Sir is going to address all on fundamentals of machine learning algorithms, covering a different application areas, signal, biomedical image processing and all. So that session will be around 11:30 to 12:30 or 12:45 like this. In the afternoon, we are having a topic titled Feature Extraction and Dimensionality Reduction Techniques. So that is going to be taken care by Dr. Sunil Kumar. He is a postdoctoral at Norwegian University. Right now, he is working with Belgium, in Belgium. So as of now, this is the tomorrow's schedule. So I request all the participants, tomorrow morning, as the schedule was a little bit tight tomorrow, and we have 3 sessions. The first session is going to start sharp by 10 a.m. So kindly requesting all of you to log in by 9:50 or so. And on the other hand, I also request the participants, if you are having any doubts relevant to machine learning or any doubts relevant to your research work, kindly, if you can come out with them, we'll try to get them resolved with the resource persons whom are going to address in the forthcoming 5 days. So please kindly make use of this platform in the right way in getting your all problems or research issues getting resolved. So I thank you one and all participants for your patient listening. Thank you, Suresh Sundaram sir, for your valuable enlightenment today. Thank you, sir.
Thank you. And I think you're recording the thing, right? Will it be shared to the participants? Because I saw some messages say they want a recording.
Hello, sir.
Sridhar sir, hello? No,
Sir,
there are
your
some
voice is
comments
getting disconnected
on
in
the
the
chat
sir, please tell,
box
sir, please
saying,
tell.
no.
What if
The participants are actually. So are you planning to do the recording and send it to them, or is it kept internal actually?
Coordinators, please share the recorded thing. Yeah, somebody is asking, sir.
So you can decide.
Yes, sir. Yes, sir. Now, if at all, sir, if you or the resource persons permit us to share your recorded thing, we are going to share, sir. Otherwise, we will be sharing the PPTs and other materials that already we have disclosed to the participants.
Right. So that should not be a
Your voice is getting disconnected. Hello? Hello?
Yeah, I also, because I also, yeah, hello. Able to hear? Hello?
Your voice is getting broken, sir. Broken. It's getting continuously broken.
Okay. I will just stop now.
I guess there might be some
Now is okay.
signal problem or network issue.
Yeah. So workshop, I really enjoyed the session. Okay. And I would like to wish all the best for the remaining forthcoming sessions and probably for any future opportunities. I would definitely be, helpful. Okay. All right. And even students can.
Thank you very much, sir. Thank you very much.
Yeah. And even students can feel free to email me any queries, okay, so that we can resolve. Okay.
Great, sir.
Okay.
Great, sir. In fact, we are going to share your mail ID to the participants, sir.
Yeah. Okay. Fine.
Okay, sir. Thank you, sir. Thank you very much.
All right. So I'm logging out then. Okay. Thank you. Yeah.
Okay, sir. Okay, sir. Thank you, sir. Thank you very much.
Yeah.
Thank you very much, sir.
Thank you.
Right. My request to the participants, kindly log in by 9:50 a.m. tomorrow morning. Thanks for your patient listening. Nacharya sir, you can wind up the schedule for today.
Yes, sir. Thank you, sir.
Right, sir.